All right, let's dive right in. If you've ever looked at an AC circuit problem, the ones with all the sine waves and differential equations, it can feel like you're staring into a total mess. But what if I told you there's a way to make all of that nasty calculus just disappear? Welcome to one of the most powerful and honestly elegant shortcuts in all of electrical engineering.
This right here, this is the key to everything we're about to cover. It's an idea called the phasor transformation. I want you to think of it like putting on a special pair of goggles. The moment you put them on, that chaotic, wavy world of AC circuits, it suddenly becomes clear. It becomes simple. Heck, it becomes algebra.
So, before we put on our magic goggles, let's just take a moment to appreciate the problem we're actually up against. See, AC circuits are driven by sources that are constantly oscillating, creating these endless waves of voltage and current that ripple through every single component. It's a dynamic, messy reality.
Now, there is one little beacon of hope in all this wavy chaos. If you feed a sine wave into a linear circuit, guess what comes out? Another sine wave. And this is the crucial part. It has the exact same frequency as the one you put in. That one single fact, it simplifies our job enormously.
So think about it. If we already know the shape of the output wave and its frequency, what's left to find? Well, our entire mission boils down to just two numbers. First, how big is the wave? That's its maximum amplitude. And second, how is it shifted in time compared to the input? That's what we call the phase angle. That's it, just two things.
And here is the payoff, all in one image. On the left, you've got the time domain equation. See how it's a function of t? It's always changing, it's messy. But look to the right. That's what we see with our goggles on. We get a phasor. All that wavy complexity is just gone. We've captured everything we need, the peak amplitude, Vm, and that phase shift, phi, in one clean, static package. So much better, right?
All right, it's time. Let's actually put on those frequency domain goggles and see how this amazing transformation works. We're officially leaving the time domain behind and stepping into a whole new world, the frequency domain.
So what exactly is a phasor? Well, it's pretty simple, really. It's a complex number that's designed to do just one job, to snatch the only two pieces of info we care about, the amplitude and the phase angle, and package them together for us. It elegantly ignores everything else, like the frequency, because we already know that doesn't change.
And this is the trade-off. Let me tell you, it's the best deal you're ever going to get in engineering. In the frequency domain, all that calculus, derivatives and integrals, they turn into simple multiplication and division. So we are literally trading painful differential equations for some pretty straightforward algebra. It's an incredible upgrade.
Okay, so we've got our goggles on, and the world looks a little different. Resistors, capacitors, inductors, they don't quite look the same anymore. Instead, we see this new, unified concept that rules everything. So let's meet impedance.
Impedance, which we write with a Z, is basically the frequency domain's version of resistance. Remember Ohm's law? R equals V over I? Well, impedance is just the voltage phasor divided by the current phasor. And yet, you guessed it, it's also measured in ohms, which should make it feel a little bit more familiar.
Now this table, this is our Rosetta Stone. It's our guide to this new world. It shows how each component looks through our goggles. A resistor's impedance? Well, it's just its resistance, R. Nice and simple. But for inductors and capacitors, things get interesting. Their impedance actually depends on the frequency of the wave, omega, and that's what creates those famous phase shifts we were talking about.
So the components look a little different, sure, but here's the absolute best part. Even though we're in this new world, we don't need a new map. All the old rules of circuit analysis, they still apply.
And I'm serious, your entire circuit analysis toolkit is still totally valid. Kirchhoff's laws, they work with phasors. Combining components in series or parallel, you just add up the impedances, Z, instead of the resistances, R. Even the more advanced stuff, like finding Thevenin and Norton equivalents, works exactly the same way. All you do is swap out R for Z. How cool is that?
Okay, theory is great, but let's apply this to a really important device, the transformer. These things are everywhere, from the power grid to your phone charger, and analyzing them used to be a real headache, but not anymore. Not for us.
In the world of phasors, the really complex behavior of an ideal transformer, it all boils down to a single, beautifully simple number. We don't have to worry about magnetic flux or mutual inductance. It's all about the turns ratio.
And there it is. The turns ratio, which we call A, is just the number of wire turns on the output coil divided by the number of turns on the input coil. That's it. This one number is the key to everything.
So, one of a transformer's main jobs is to make the impedance of whatever is connected on one side look totally different to the circuit on the other side. And with our frequency domain goggles on, calculating this reflected impedance becomes incredibly simple.
And here's the final magic trick. The input impedance that the source sees is just the load impedance, ZL, divided by the turns ratio squared. That's the entire calculation. A simple bit of algebra completely replaces some very complex magnetic field analysis. It's amazing.
Let's just pause on that for a second. We just analyzed a transformer, a fundamentally complex electromagnetic device. And we did the whole thing with basic algebra. We completely sidestepped all the differential equations that actually govern its behavior in the real world. That is the power of the phasor.
So that really leaves us with a final thought, doesn't it? This phasor transformation, it isn't just a clever trick for circuits. It's a whole way of thinking. It's about finding a new perspective, a different lens where a really hard problem suddenly becomes easy. So the real question is, what other complex problems, maybe in science or engineering, or even in life, are just waiting for us to find the right pair of goggles?